Okay, question number 5. The binding energy per nucleon against nucleon number graph of some common nucleides is shown below. So we have all this here. So number A, identify the most stable nucleid. Explain your answer. Use a graph to estimate the binding energy of the nucleus of carbon. Okay, so here I have a mistake over here. It's 12 carbons. Okay, for carbon, use the graph to estimate the energy released in following fusion reactions. And finally, the fusion reaction shown in C is one of the many that occur in the interior of star. So state the condition necessary to initiate such reactions in stars. Okay. First, we have to identify the most stable nuclei. So means you have the most energy. You need to give most of the energy to break them into parts. So that's why we call it stable. Okay. If you easy to break them into all the parts, means that it is not stable. So which is at here, which is our 5626 ferrum. Okay, it's our ferrum. So why? Because it has the maximum value of binding energy. Okay, it has a maximum value of binding energy. So B, use a graph to estimate the binding energy of the 12-16 carbon. So where is my carbon over here? So my carbon is here. This is my carbon. Okay, so the carbon here is around, if you look at the graph, it's around 12. Okay, it's around 12. So if I want to find the binding energy of the nucleus of carbon 12, now you have to do like this. So binding energy is equal to 12, okay, times 10 to the power negative 13. Now I have to times back the number of nucleon, which is for carbon is 12. Okay, why? Now look at the here carefully, is per nucleon. So whatever this graph we plot is actually per nucleon. Okay, so means that if you want to find the real binding energy, you need to times back the nucleon that carried by each nucleus. Okay, so in this case carbon 12 is have 12 over here, so I should have 1.44 times 10 to the power negative 11 joules. Okay, so part C, I have to use a graph to estimate the energy released in the following fusion reactions. Okay, so hydrogen 2 and 1. So where is my hydrogen over here? Where is my hydrogen? So my hydrogens will be at somewhere here. This is my small hydrogen here, where it have a value around 1. So let us make it as 1. Okay, so the binding energy for hydrogen, okay, binding energy for 2,1 hydrogen is equal to 1 times 10 to the power negative 13 times 2. So here why is 2 is here, because it's when I get it from the graph is per nucleon. So now I have 2 nucleon in that hydrogen, so I have 2 times 10 to the power negative 13 joules. Okay, now then I have to find what is the binding energy. Oops, sorry. Of to helium. Okay, because I need to calculate the process to know that what is the energy release of this whole equation. So for helium is hidden somewhere here. Okay, it's hidden somewhere here. So it's roughly around, let's say it's around 11. Okay, it's around 11. So 11 times 10 to the power times 10 to the power negative 13 times 4. Okay, times 4. So means I have 4.4 times 10 to the power negative 12 joules. Okay, negative 12 joules. Okay, so the energy release is equal to 2 times 10 to the power negative 13 joules, which is the energy binding energy for one hydrogen. But in this equation we have 2 hydrogen, means I have to times the 2. Okay, minus away the binding energy is 4.4 of helium times 10 to the power negative 12 joules. Okay, so I should have roughly around 4 times 10 to the power negative 12 joules, which is the binding energy of the energy release of the equation. Okay, whereas two hydrogens will become one helium. Okay, now part D is say that where this is the process that which happens in stars. Okay, so means that how actually we can do to combine it and we have a helium. Okay, so you have to understand that we have to have a very high temperatures and also pressure so that you can have this happen. So that's why helium gas is a natural gas. It cannot be produced on Earth. Okay, you have to produce in other planets because we need high temperatures and high pressures.